Equipped with his five senses, man explores the universe around him and calls the adventure science. Edwin Hubble. The James Webb Space Telescope and the Big Bang, rethinking our cosmic origins. Introduction, a new era of exploration ****. The launch of the James Webb Space Telescope, JWST, marked the beginning of a revolutionary era in astronomical exploration. Designed to look further back in time than any previous telescope, the JWST has the ability to peer into the universe's infancy, observing galaxies and stars as they formed over 13 billion years ago. Its unprecedented resolution and sensitivity have provided a clearer picture of the early universe, but with these revelations come challenges to long-standing scientific theories, particularly the Big Bang theory. For decades, the Big Bang has been the dominant cosmological model for explaining the origin and evolution of the universe. This theory posits that the universe began as a singular point, or singularity, which expanded rapidly in an event known as the Big Bang. As the universe cooled, subatomic particles formed, leading to the creation of atoms and, eventually, stars and galaxies. While the Big Bang theory has been supported by significant evidence, including the cosmic microwave background radiation, CMB, and the observed expansion of the universe, recent observations by the JWST have raised questions that require a re-examination of some of its details. The James Webb Space Telescope, a technological marvel. The JWST was designed with the primary goal of uncovering the mysteries of the early universe. Its advanced infrared capabilities allow it to peer through cosmic dust and gas, revealing structures and phenomena that were previously hidden. This telescope was positioned at the second Lagrange point, L2, a stable spot in space where it could observe the universe without interference from Earth's atmosphere or radiation. Equipped with a 6.5-meter primary mirror, JWST can collect and analyze light that has traveled billions of years to reach us, effectively looking back in time to see the first galaxies forming after the Big Bang. The most striking aspect of the JWST's discoveries is the detection of galaxies that seem to contradict our understanding of the universe's infancy. These galaxies, discovered in what are believed to be the first few hundred million years after the Big Bang, are far more massive and mature than previously thought possible. Such findings challenge our models of how galaxies form and evolve and cast doubt on the timeline that the Big Bang theory proposes. #The challenge to the Big Bang theory, galaxies too early, too complex. One of the fundamental predictions of the Big Bang theory is that the early universe should have been a simple, relatively homogeneous environment, where stars and galaxies slowly coalesced over time. According to this model, it should have taken hundreds of millions of years for galaxies to form, with the first stars appearing around 100 to 200 million years after the Big Bang. However, the JWST has observed galaxies in the first few hundred million years that appear to be fully formed and highly complex, raising questions about how such structures could exist so soon after the universe began. These early galaxies, some detected only 300 million years after the Big Bang, possess features that defy expectations. They are not just small, fledgling galaxies, they are large, mature systems with significant star formation rates and well-formed structures. Some even appear to contain massive black holes at their centers, suggesting that these cosmic giants formed and evolved far faster than current models can account for. The implications of these discoveries are profound. If galaxies could form so quickly after the Big Bang, then our understanding of cosmic evolution may need to be revised. It raises the possibility that the processes driving star and galaxy formation were more efficient or that alternative mechanisms played a role in shaping the early universe. #Cosmic timelines and the need for new theories. The JWST's data has forced astronomers to confront the possibility that the universe's evolution may not have followed the straightforward path outlined by the Big Bang theory. One possibility is that the early universe was far more dynamic and chaotic than previously thought. This could mean that stars and galaxies formed under extreme conditions that accelerated their development, or it might suggest that our models for understanding the behavior of matter and energy in the early universe need to be reworked. Another theory gaining traction is that we might need to revisit the assumptions made about the distribution of dark matter and dark energy in the early universe. Dark matter, which interacts with regular matter through gravity but does not emit light, is believed to play a crucial role in the formation of galaxies. If dark matter was clumping together more efficiently in the early universe, it could have accelerated the formation of galaxies. Additionally, the influence of dark energy, which is driving the accelerated expansion of the universe, could have affected how matter coalesced in the aftermath of the Big Bang. However, even these adjustments may not fully explain the observations made by the JWST. Some researchers are beginning to explore more radical possibilities, such as alternative cosmological models that differ from the traditional Big Bang narrative. These models may offer new explanations for how galaxies could form so quickly and mature so rapidly in the early universe. #Alternative cosmological models, beyond the Big Bang. Several alternative models to the Big Bang have been proposed over the years, though none have achieved the same level of acceptance. The JWST's findings have reignited interest in these models, as scientists look for new ways to explain the universe's earliest moments. One of the most intriguing alternatives is the idea of a cyclic universe, where the universe undergoes repeated cycles of expansion and contraction, with each cycle representing a new beginning. In this model, the Big Bang is not a singular event but part of a larger process in which the universe is constantly being reborn. Other theories propose modifications to the inflationary period of the Big Bang. Inflation theory suggests that the universe underwent an exponential expansion in the first fraction of a second after the Big Bang. This rapid inflation could explain why the universe appears so homogeneous on large scales. However, some cosmologists are exploring variations of inflation theory, where the inflationary period was more complex, leading to faster galaxy formation in the early universe. Another possibility is the multiverse hypothesis, which posits that our universe is just one of many that exist in a larger multiverse. In this framework, different universes may have different physical laws or initial conditions, some of which might allow galaxies to form more quickly. While this idea remains speculative, it offers a potential explanation for the JWST's findings. #Dark matter and the mystery of cosmic formation. In any discussion about the early universe and galaxy formation, the role of dark matter cannot be overlooked. While dark matter remains one of the greatest mysteries of modern astrophysics, it is widely accepted that it plays a crucial role in the formation of large-scale structures in the universe. The JWST's observations of early galaxies have spurred scientists to rethink how dark matter might have influenced the rapid formation of these systems. Current models of galaxy formation rely on the idea that dark matter halos, dense regions of dark matter, provided the gravitational scaffolding for galaxies to form. As gas and dust collapsed under the influence of gravity, stars were born and galaxies grew. However, the speed and scale at which the galaxies observed by JWST formed suggest that dark matter may have behaved differently in the early universe. One hypothesis is that dark matter was more concentrated in the early universe, creating deeper gravitational wells that accelerated the formation of galaxies. Alternatively, it could be that dark matter particles interacted more strongly with regular matter in the early universe, helping to trigger star formation at an accelerated rate. Another possibility is that the nature of dark matter itself is more complex than we currently understand. Some physicists are exploring the idea that dark matter may consist of more than one type of particle, or that it might have properties that change over time. These variations could explain why galaxies in the early universe formed so quickly, as well as other puzzling observations. #The role of black holes in early galaxy formation. One of the most surprising findings from the JWST is the presence of supermassive black holes at the centers of some of the earliest galaxies. These black holes, with masses millions or even billions of times that of the Sun, are typically found in the centers of mature galaxies like our Milky Way. The discovery of such massive black holes in galaxies that formed only a few hundred million years after the Big Bang challenges our understanding of how black holes grow. current models suggest that black holes form when massive stars collapse at the end of their life cycles. Over time, these black holes can grow by accreting gas and merging with other black holes. However, this process is thought to take billions of years, making it difficult to explain the existence of such massive black holes in the early universe. One possible explanation is that black holes in the early universe grew more quickly than previously thought, perhaps due to the abundance of gas and matter in the universe's infancy. Another possibility is that these black holes formed through a different mechanism, such as the direct collapse of massive gas clouds without first forming stars. The presence of these black holes also raises questions about their role in the formation and evolution of galaxies. Some scientists believe that black holes may have played a key role in shaping the structure of early galaxies, influencing star formation and galaxy growth through their intense gravitational pull and energetic jets. #Conclusion, a new chapter in cosmic understanding. The discoveries made by the James Webb Space Telescope have opened a new chapter in our understanding of the universe. While the Big Bang theory remains the dominant framework for explaining the origin and evolution of the cosmos, the JWST's observations have highlighted gaps in our knowledge and raised important questions about the early universe. As scientists continue to analyze the data from JWST, it is clear that we are on the brink of new discoveries that could reshape our understanding of cosmic history. Whether these discoveries will lead to modifications of the Big Bang theory, the development of alternative models, or a deeper understanding of dark matter and black holes, one thing is certain: the universe still holds many mysteries waiting to be uncovered. The quest for knowledge, driven by the observations of telescopes like JWST, brings us closer to answering fundamental questions about our place in the cosmos. As we delve deeper into the mysteries of the universe, we are reminded of Carl Sagan's words: "We are a way for the cosmos to know itself." Each discovery, each new piece of data, brings us closer to understanding the profound and beautiful complexity of the universe we inhabit. #The expanding universe, new questions, new horizons. The James Webb Space Telescope, JWST, has not only provided a glimpse into the distant past, but it has also reignited a debate about the very fabric of our universe's evolution. One of the central concepts of the Big Bang theory is the expansion of the universe, a notion initially confirmed by the observation that distant galaxies appear to be moving away from us, a phenomenon known as redshift. This discovery led to the formulation of Hubble's law, which states that galaxies are receding from each other at speeds proportional to their distance. The further away a galaxy is, the faster it seems to be moving, suggesting that the universe itself is expanding. However, the precise rate of this expansion, known as the Hubble constant, has been a subject of significant debate, and the JWST's observations have added to the complexity. Recent measurements of the expansion rate using various methods, such as studying the CMB or analyzing distant supernovae, have yielded conflicting results. Some methods suggest a faster expansion rate, while others indicate a slower one. This discrepancy, known as the Hubble tension, has puzzled cosmologists for years, and the data from JWST may offer clues to resolve this issue or introduce entirely new puzzles. The Hubble tension, a crisis or an opportunity? The Hubble tension represents one of the most significant challenges to the Big Bang theory in recent times. Before the launch of JWST, astronomers were already grappling with the fact that different methods of measuring the expansion rate of the universe provided inconsistent values for the Hubble constant. On one hand, measurements based on observations of the CMB, the faint afterglow of the Big Bang, suggest a slower rate of expansion. On the other hand, observations of more recent phenomena, such as supernovae in galaxies, suggest a faster rate. This discrepancy has led some to question whether our current understanding of the universe's expansion is incomplete. Could there be unknown factors at play that are influencing the way we measure cosmic distances? Or perhaps the laws of physics themselves behave differently over time and space, altering our perception of the universe's expansion? The JWST's observations have only deepened this mystery. By providing detailed views of distant galaxies and their redshifts, the telescope offers new data to help refine our measurements of the Hubble constant. Yet, rather than resolving the tension, these new observations have highlighted even more inconsistencies. Some of the early galaxies observed by JWST seem to defy the expected relationship between their redshift and their distance, suggesting that the universe's expansion rate may not be as uniform as we once thought. This has led to speculation about whether new physics might be required to explain the Hubble tension. One possibility is that dark energy, the mysterious force that drives the accelerated expansion of the universe, may have evolved over time. Another possibility is that our understanding of gravity itself needs to be revised, with some proposing modifications to Einstein's theory of general relativity. ### Dark energy, the mysterious force behind cosmic acceleration. Dark energy remains one of the greatest mysteries in cosmology. This invisible force, first discovered in the late 1990s, is responsible for the accelerated expansion of the universe. Despite its name, dark energy is not a form of matter but rather a property of space itself. It pushes galaxies apart, counteracting the gravitational pull of matter and causing the universe to expand at an ever-increasing rate. While dark energy is now a well-established component of the universe, accounting for roughly 70% of the universe's total energy, its nature remains elusive. The standard model of cosmology, known as lambda-CDM, lambda cold dark matter, assumes that dark energy is constant and unchanging, described by the cosmological constant, lambda. However, the JWST's observations have raised questions about whether dark energy might be more dynamic than previously thought. One of the key challenges in understanding dark energy is its impact on the expansion rate of the universe. If dark energy has remained constant throughout cosmic history, then the universe should have expanded in a predictable way. However, the discrepancies in the Hubble constant measurements suggest that the behavior of dark energy may have changed over time. Some cosmologists speculate that dark energy could be evolving, meaning that its strength might vary depending on the age or size of the universe. If dark energy is indeed evolving, it could explain why early galaxies observed by JWST appear to defy our expectations. These galaxies may have formed in a universe where the effects of dark energy were weaker or stronger than they are today, leading to different rates of cosmic expansion. This would not only challenge the lambda-CDM model but also open the door to new theories about the nature of dark energy and its role in shaping the cosmos. ### The multiverse hypothesis, beyond the limits of our universe. The idea of a multiverse, once relegated to the realm of science fiction, has gained increasing traction in cosmology. While the concept of multiple universes is still highly speculative, the JWST's findings have reignited interest in the possibility that our universe is just one of many. In a multiverse scenario, different universes may have different physical laws, constants, and even different rates of expansion. Some universes might experience rapid galaxy formation, while others might evolve more slowly. The idea of a multiverse could help explain why the JWST has observed galaxies that seem to form faster than what the Big Bang theory would predict. Perhaps these galaxies exist in regions of the multiverse where the conditions for galaxy formation are more favorable. The multiverse hypothesis also provides a potential solution to the Hubble tension. If our universe is part of a larger multiverse, then the discrepancies in the Hubble constant measurements could be a result of variations in the properties of different universes. For example, the part of the multiverse we inhabit might have a different rate of expansion than other regions, leading to the observed inconsistencies. While the multiverse hypothesis is far from being proven, it offers an intriguing avenue for exploration, particularly in light of the JWST's unexpected discoveries. It challenges the notion that the Big Bang was a singular event that gave rise to all of space and time and instead suggests that the cosmos may be far more complex and expansive than we can currently comprehend. ### The role of quantum physics in early universe formation. As we delve deeper into the early universe, we encounter the realm of quantum physics, where the classical laws of physics break down, and new, often counterintuitive, phenomena take over. Quantum physics plays a central role in understanding the universe's earliest moments, particularly during the first fractions of a second after the Big Bang, known as the Planck epoch. During this epoch, the four fundamental forces of nature, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, are believed to have been unified into a single force. As the universe expanded and cooled, these forces gradually broke apart or decoupled, giving rise to the distinct forces we observe today. Quantum fluctuations during this early period are thought to have seeded the formation of galaxies and large-scale structures. These tiny fluctuations in energy density, magnified by the rapid expansion of space during the inflationary period, eventually grew into the stars, galaxies, and clusters we see today. The JWST's ability to observe these early structures in unprecedented detail provides a unique opportunity to test predictions made by quantum cosmology. One of the most intriguing aspects of quantum physics in the context of the early universe is the concept of quantum foam, a state of spacetime thought to exist at the smallest scales, where space and time themselves become unstable and fluctuating. Some theorists believe that this quantum foam could give rise to multiple universes, providing a potential explanation for the multiverse hypothesis. The JWST's observations of early galaxies may offer new insights into the role of quantum physics in shaping the cosmos. By studying the distribution and properties of these galaxies, scientists hope to gain a better understanding of how quantum fluctuations influence the formation of structures in the universe and how the laws of quantum physics continue to shape the evolution of the cosmos. ### Black holes as cosmic architects, the early role of supermassive black holes. The presence of supermassive black holes at the centers of early galaxies observed by the JWST has led to renewed interest in the role these enigmatic objects play in shaping the universe. Black holes are not merely destructive forces that consume everything in their vicinity, they are also fundamental architects of cosmic structures, influencing the formation and evolution of galaxies in profound ways. The discovery of supermassive black holes in galaxies that formed only a few hundred million years after the Big Bang suggests that these objects may have played a more significant role in the early universe than previously thought. Current models of galaxy formation assume that black holes grow over billions of years, accreting gas and merging with other black holes. However, the JWST's findings indicate that some black holes reached enormous masses much earlier than expected, challenging our understanding of how these objects form and grow. One possibility is that black holes in the early universe formed through a process known as direct collapse, where massive clouds of gas collapse directly into black holes without first forming stars. This process could explain how supermassive black holes were able to grow so quickly in the universe's infancy. Alternatively, these black holes may have formed through the mergers of smaller black holes, which could have been more frequent in the densely packed early universe. The presence of these black holes also raises questions about their influence on the galaxies that surround them. Supermassive black holes are known to produce powerful jets of energy that can shape the structure of galaxies, regulating star formation and driving gas out of galaxies. In the early universe, these jets may have played a crucial role in shaping the evolution of galaxies, helping to create the large, mature systems observed by the JWST. #Conclusion, a new frontier in cosmic exploration. The discoveries made by the James Webb Space Telescope have opened a new frontier in our exploration of the universe. While the Big Bang theory has long been the cornerstone of cosmology, the JWST's findings have raised new questions and challenges that require us to rethink our understanding of the cosmos. Whether through the refinement of existing theories or the development of new models, we are on the cusp of a new era in our quest to understand the universe's origins and evolution. As we continue to explore the cosmos with tools like the JWST, we are reminded that science is a constantly evolving process, driven by curiosity and the desire to understand the unknown. The universe, in all its complexity and beauty, continues to surprise us, and each new discovery brings us closer to unraveling its deepest mysteries. In the words of Carl Sagan, somewhere, something incredible is waiting to be known. The JWST is bringing us ever closer to that incredible knowledge, pushing the boundaries of what we know and inspiring future generations to continue the journey of cosmic discovery. ### The Cosmic Web, Unveiling the Large-Scale Structure of the Universe. One of the most remarkable aspects of the universe, revealed by large-scale surveys and telescopes like the James Webb Space Telescope, JWST, is its intricate and interconnected structure, often referred to as the cosmic web. This vast network of galaxies, dark matter, and gas extends across billions of light-years, forming a filamentous structure that resembles a spider's web on a cosmic scale. The cosmic web is the scaffolding of the universe, guiding the formation of galaxies and clusters while defining the vast voids of space. The cosmic web's complexity is a direct result of billions of years of cosmic evolution, shaped by gravity and the mysterious forces of dark matter and dark energy. The JWST, with its ability to observe distant galaxies in unprecedented detail, has allowed scientists to study the early stages of the cosmic web's formation, offering new insights into how the large-scale structure of the universe developed. What the JWST has shown us is that the cosmic web may have formed earlier than previously thought, with galaxies organizing into filaments and clusters within the first billion years after the Big Bang. These findings challenge the conventional timeline, suggesting that the processes of galaxy formation and large-scale structure development occurred at a much faster pace than our models predicted. ### Dark Matter and the Cosmic Web, the Invisible Hand Guiding Structure. At the heart of the cosmic web is dark matter, an invisible form of matter that does not interact with light but exerts a powerful gravitational influence on regular matter. Dark matter acts as the backbone of the cosmic web, shaping the distribution of galaxies and clusters. Without dark matter, the universe would look very different, galaxies would not have formed in the same way, and the cosmic web as we know it would not exist. One of the key questions that the JWST has helped address is how dark matter influenced the formation of the cosmic web in the early universe. By observing distant galaxies and their distribution, the JWST has provided new evidence for the role of dark matter in creating the first structures in the universe. It appears that dark matter began to clump together into massive halos very early on, providing the gravitational pull needed to draw in gas and form galaxies along the filaments of the cosmic web. The JWST has also allowed scientists to study the interaction between dark matter and regular matter in greater detail. Observations of early galaxy clusters show that dark matter played a crucial role in accelerating the growth of these structures, acting as the scaffolding upon which galaxies formed. This has led to new theories about how dark matter may have behaved differently in the early universe compared to today, potentially clumping together more efficiently and forming denser regions of the cosmic web. ### The Missing Link, Warm Dark Matter and Structure Formation. While the existence of dark matter is widely accepted, its exact nature remains one of the greatest mysteries in astrophysics. Current models suggest that dark matter is cold, meaning that it moves slowly and interacts weakly with regular matter. However, recent observations by the JWST have prompted some scientists to explore the possibility that dark matter might not be entirely cold. Instead, there may be a component of warm dark matter, particles that move more quickly and could influence structure formation in unique ways. The idea of warm dark matter could help explain some of the JWST's unexpected findings, particularly the rapid formation of galaxies and structures in the early universe. Warm dark matter particles would have slightly more kinetic energy than cold dark matter, allowing them to diffuse more easily through space. This would lead to a smoother, less clumpy distribution of dark matter, which could result in the faster formation of galaxies along the filaments of the cosmic web. While warm dark matter remains a speculative idea, the JWST's observations have provided new motivation to explore this possibility. By studying the distribution of galaxies and dark matter in the early universe, scientists hope to determine whether warm dark matter played a role in shaping the cosmic web and accelerating the formation of large-scale structures. ### The JWST's Deep Field Images, a window into cosmic evolution. One of the most iconic and awe-inspiring aspects of the JWST's mission has been its deep field images, detailed snapshots of the universe that reveal thousands of galaxies in a single frame. These images provide a window into the universe's history, capturing galaxies at various stages of evolution and offering a glimpse of what the cosmos looked like billions of years ago. The deep field images taken by the JWST have been particularly important for studying the formation of the cosmic web. By observing galaxies at different distances and redshifts, scientists can trace the growth of large-scale structures over time. These images reveal the intricate filaments of the cosmic web, with galaxies clustered along its tendrils and massive voids stretching between them. The JWST's deep field images also offer new insights into the formation of galaxy clusters, the largest gravitationally bound structures in the universe. These clusters, which contain hundreds or even thousands of galaxies, are the intersections of the cosmic web's filaments. The JWST has observed galaxy clusters forming in the early universe, providing valuable data on how these massive structures came together and evolved over billions of years. One of the most surprising findings from the JWST's deep field images is the discovery of galaxy clusters that appear far more evolved than expected, even in the early universe. Some of these clusters exhibit signs of mature, well-formed galaxies, complete with complex structures like spiral arms and central bulges. This suggests that the processes of galaxy formation and cluster development may have occurred much more rapidly than previously thought, potentially reshaping our understanding of cosmic evolution. ### The role of feedback mechanisms in galaxy evolution. While the cosmic web provides the framework for galaxy formation, other processes play a crucial role in shaping the evolution of galaxies over time. One of the most important of these processes is feedback, the interaction between stars, black holes, and the gas within galaxies that regulate star formation and the growth of galaxies. The JWST has provided new insights into the role of feedback mechanisms in the early universe, particularly in relation to supermassive black holes and their influence on galaxy evolution. Observations of early galaxies have revealed powerful jets of energy being emitted by black holes, which can have a profound effect on the surrounding gas. These jets, known as active galactic nuclei, AGN, can heat up the gas in a galaxy and prevent it from collapsing to form new stars, effectively quenching star formation. Feedback from black holes is thought to play a key role in regulating the growth of galaxies, ensuring that they do not become too massive too quickly. The JWST's observations of AGN in early galaxies suggest that these feedback processes were already at work in the universe's infancy, helping to shape the evolution of galaxies and the cosmic web. In addition to black hole feedback, the JWST has also provided new data on the role of supernovae in galaxy evolution. Supernovae, explosions of massive stars at the end of their life cycles, release vast amounts of energy and material into space, enriching the interstellar medium with heavy elements. This material is crucial for the formation of new stars and planets, and the energy released by supernovae can drive powerful winds that shape the structure of galaxies. The JWST's observations of early star-forming galaxies have shown that supernovae were likely a major driver of galaxy evolution in the early universe. By studying the distribution of supernovae and their impact on the surrounding gas, scientists are gaining a better understanding of how feedback processes influenced the growth of galaxies and the development of the cosmic web. ### The first stars, JWST's glimpse into cosmic dawn. One of the JWST's most ambitious goals is to observe the first stars that formed after the Big Bang, a period known as cosmic dawn. These stars, known as population 3 stars, were the first to shine in the universe, made almost entirely of hydrogen and helium. They were massive, short-lived, and played a crucial role in shaping the early universe by producing the first heavy elements through nuclear fusion. The JWST's infrared capabilities have allowed it to peer further back in time than any previous telescope, offering the first glimpses of these primordial stars. Observing population 3 stars is a challenging task, as they are thought to have existed only for a brief period before being replaced by later generations of stars. However, the JWST's sensitivity to infrared light has enabled it to detect the faint signatures of these early stars, providing valuable data on their properties and their impact on the universe. The discovery of population 3 stars by the JWST has important implications for our understanding of cosmic evolution. These stars were responsible for producing the first heavy elements, such as carbon, oxygen, and iron, which are essential for the formation of planets and life. By studying these stars, scientists hope to gain new insights into the processes that led to the formation of galaxies, stars, and planets in the early universe. The JWST's observations of population 3 stars have also raised new questions about the timeline of cosmic dawn. While previous models suggested that these stars formed around 100 million years after the Big Bang, the JWST has observed signs of star formation even earlier than expected. This has led to speculation that cosmic dawn may have occurred sooner than previously thought, potentially reshaping our understanding of the universe's first light. ### The future of cosmic exploration, New Horizons with the JWST. As the James Webb Space Telescope continues its mission, the data it collects will undoubtedly lead to even more discoveries that challenge our understanding of the universe. The telescope's ability to observe the most distant and ancient objects in the cosmos is providing a new window into the universe's history, offering insights into the formation of galaxies, stars, and the cosmic web. The JWST's findings have already prompted scientists to rethink some of the most fundamental aspects of cosmology, from the timeline of galaxy formation to the nature of dark matter and dark energy. As new theories are developed and tested against the telescope's observations, we may be on the verge of a new paradigm in our understanding of the universe. The exploration of the cosmos is a journey that has only just begun. With each new discovery, we are reminded of the vastness and complexity of the universe, and of the profound questions that remain unanswered. The JWST is not just a tool for observing the distant past, it is a beacon of discovery, guiding us toward a deeper understanding of the cosmos and our place within it. As we continue to push the boundaries of knowledge, the words of Carl Sagan echo in our minds: somewhere, something incredible is waiting to be known. The James Webb Space Telescope is helping us uncover those incredible truths, and the future of cosmic exploration promises to be filled with even more wonder and discovery. ### The evolution of galaxies, from cosmic dawn to the modern universe. As the James Webb Space Telescope, JWST, continues to unveil the secrets of the cosmos, its observations have dramatically shifted our understanding of galaxy evolution. From the first, primitive galaxies formed during the era known as cosmic dawn to the vast, mature galaxies seen today, the JWST has revealed a more complex and dynamic history than previously imagined. Galaxies, often described as islands of stars, gas, and dark matter, have been evolving for billions of years. Their formation and growth are intertwined with the overall structure of the universe, driven by gravitational interactions and the influence of dark matter. The JWST's ability to observe galaxies at various stages of their development, from the earliest epochs to the present day, allows astronomers to piece together the intricate puzzle of how galaxies form, evolve, and interact with their surroundings. One of the most significant contributions of the JWST is its ability to peer into the era of reionization, a time when the first galaxies and stars began to ionize the neutral hydrogen that filled the universe. This process transformed the universe from an opaque fog to the transparent, star-filled cosmos we see today. The galaxies observed by JWST in this period are often small and faint, but they represent the building blocks of more massive galaxies that would dominate later cosmic epochs. ### The early galaxies, building blocks of the cosmos. The JWST has provided stunning images of galaxies that formed just a few hundred million years after the Big Bang. These early galaxies are much smaller and less structured than those we observe today, often lacking the spiral arms and well-defined bulges typical of mature galaxies. However, they are incredibly dynamic environments, filled with intense star formation driven by processes that shaped the future of the cosmos. These primordial galaxies, often referred to as proto-galaxies, are the seeds from which larger galaxies grew. In the early universe, galaxies collided and merged frequently, driven by the gravitational pull of dark matter. The JWST has captured these interactions in unprecedented detail, allowing scientists to study how these mergers influenced the formation of larger galaxies. These galactic collisions played a crucial role in shaping the universe, driving star formation and helping to build the complex structures we observe in galaxies today. One of the surprising findings from the JWST's observations is the discovery of galaxies that are far more massive and mature than expected at such early stages of cosmic history. Some of these early galaxies are already well formed, with significant amounts of dust and heavy elements, materials that are usually produced by multiple generations of stars. This suggests that star formation and galaxy evolution may have occurred much more rapidly in the early universe than previously thought, potentially challenging our current models of galaxy formation. ## Galaxy mergers, shaping the modern universe. As the universe evolved, galaxies continued to collide and merge, driving the growth of ever larger structures. Galaxy mergers are one of the most dramatic events in the cosmos, often triggering bursts of star formation as gas and dust are compressed during the collision. The JWST has provided new insights into the role of galaxy mergers in shaping the modern universe, capturing these events in stunning detail. One of the key questions that JWST's observations have helped to address is how these mergers influence the growth of supermassive black holes at the centers of galaxies. Supermassive black holes, with masses millions or billions of times that of the Sun, are thought to grow by accreting gas during mergers. The energy released by these black holes can have a profound impact on their host galaxies, driving powerful winds that sweep away gas and quench star formation. The JWST has observed galaxies in the process of merging, with black holes at their centers emitting intense radiation. These observations have provided new evidence for the role of galaxy mergers in feeding supermassive black holes and driving the growth of these cosmic giants. By studying these events, scientists are gaining a better understanding of how black holes and galaxies co-evolve over time. ## Star formation in the early universe, an accelerated process. One of the most surprising revelations from the JWST's observations of early galaxies is the rapid pace of star formation in the young universe. While previous models suggested that stars formed gradually over hundreds of millions of years, the JWST has shown that some galaxies in the early universe were producing stars at rates far higher than expected. These starburst galaxies were creating new stars at a pace that rivals or exceeds even the most active galaxies in the modern universe. Star formation is a complex process that depends on a delicate balance of factors, including the availability of gas, the influence of dark matter, and the presence of feedback mechanisms such as supernovae and black hole activity. In the early universe, conditions were very different from those today, with gas and dust more abundant and galaxies more prone to interactions and mergers. These factors likely contributed to the rapid pace of star formation observed by the JWST. The discovery of such intense star formation in the early universe has profound implications for our understanding of cosmic evolution. It suggests that the first few 100 million years after the Big Bang may have been a much more dynamic and chaotic period than previously thought, with galaxies rapidly forming and evolving in response to their environment. ## The role of feedback in shaping galaxies. As galaxies form stars, they also generate powerful feedback mechanisms that regulate their growth. One of the most important forms of feedback is the energy released by supernovae, explosions of massive stars at the end of their life cycles. These explosions can drive winds of gas and dust out of galaxies, slowing down or even halting star formation. The JWST has provided new insights into the role of supernova feedback in the early universe, observing galaxies where supernovae are actively shaping their environment. These observations suggest that feedback from supernovae played a crucial role in regulating star formation in the early universe, preventing galaxies from growing too rapidly and helping to shape the evolution of the cosmic web. In addition to supernova feedback, the JWST has also revealed the impact of black hole feedback on galaxy evolution. As black holes grow by accreting gas, they release enormous amounts of energy in the form of jets and radiation. This energy can heat up the gas in a galaxy, preventing it from collapsing to form new stars. The JWST's observations of active galactic nuclei, AGN, in early galaxies suggest that black hole feedback was already playing a significant role in regulating star formation in the first billion years after the Big Bang. ###distant quasars, the beacons of the early universe. One of the most fascinating discoveries made by the JWST is the observation of distant quasars, supermassive black holes that are actively accreting gas and emitting intense radiation. Quasars are some of the most luminous objects in the universe, and they can be seen across vast distances, serving as beacons of the early universe. The JWST's ability to observe quasars at redshifts greater than 7, corresponding to just a few hundred million years after the Big Bang, has provided new insights into the formation and growth of supermassive black holes. These quasars are often found in the centers of massive galaxies, where they are actively consuming gas and driving powerful jets of energy. The discovery of such massive quasars in the early universe raises important questions about how supermassive black holes grew so quickly. Current models suggest that black holes form from the collapse of massive stars, but the rapid growth of these quasars suggests that other processes, such as direct collapse or mergers, may have played a more significant role in the early universe. The JWST's observations of distant quasars also provide valuable information about the conditions in the early universe. The radiation from quasars can ionize the gas around them, creating large bubbles of ionized gas in the intergalactic medium. By studying these bubbles, scientists can gain insights into the process of reionization and how the first stars and galaxies transformed the universe. ###The future of cosmic exploration with the JWST. The James Webb Space Telescope has already revolutionized our understanding of the universe, but its mission is far from over. In the coming years, the JWST will continue to explore the most distant and ancient regions of the cosmos, providing new data that will challenge and refine our models of galaxy formation, star formation, and cosmic evolution. One of the most exciting areas of future exploration is the study of exoplanets, planets orbiting stars beyond our solar system. The JWST's advanced instruments are capable of analyzing the atmospheres of exoplanets, searching for signs of habitability and potential biomarkers. This will provide a new window into the search for life beyond Earth, offering insights into the diversity of planetary systems and the conditions that may support life. The JWST will also continue to study the large-scale structure of the universe, mapping the cosmic web in greater detail and revealing how dark matter and dark energy have shaped the evolution of the cosmos. By observing galaxy clusters, filaments, and voids, the JWST will help scientists understand how the universe's structure evolved over billions of years, offering new clues about the nature of dark matter and the role of dark energy in driving cosmic expansion. ###conclusion, a journey of discovery. The James Webb Space Telescope has taken us on an incredible journey through time and space, revealing the wonders of the universe in ways we could never have imagined. Its observations have challenged long-held assumptions about the formation and evolution of galaxies, stars, and black holes, while also opening up new avenues for exploration and discovery. As we look to the future, the JWST will continue to push the boundaries of our knowledge, offering new insights into the mysteries of the cosmos. Each new discovery brings us closer to understanding the fundamental questions of our existence. How did the universe begin? How do galaxies and stars form? And are we alone in the universe? The JWST is not just a tool for scientific discovery, it is a symbol of humanity's insatiable curiosity and our desire to explore the unknown. As we continue to unravel the secrets of the cosmos, we are reminded of the words of Carl Sagan, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. Exoplanets and the search for life, new frontiers with the JWST. One of the most anticipated aspects of the James Webb Space Telescope's JWST mission is its ability to explore exoplanets, planets that orbit stars outside our solar system. Since the discovery of the first exoplanets in the 1990s, astronomers have been captivated by the idea that planets like Earth may be common throughout the galaxy. The JWST's advanced capabilities have brought us closer than ever to answering one of humanity's most profound questions: are we alone in the universe? The JWST's powerful infrared instruments allow it to study the atmospheres of exoplanets in detail, analyzing the chemical composition of these distant worlds. By observing the light that passes through an exoplanet's atmosphere as it transits in front of its star, the JWST can detect the presence of molecules such as water vapor, carbon dioxide, methane, and even oxygen, potential indicators of habitability or life. This capability has transformed the search for extraterrestrial life from speculative theory into a scientific endeavor with real observational data. While previous telescopes, such as Hubble and Kepler, laid the groundwork by identifying exoplanets and providing basic data on their size and orbits, the JWST goes much further. Its ability to detect biosignatures, chemical indicators of life, marks a new chapter in the quest to understand the diversity of planetary systems and the potential for life beyond Earth. The discovery of habitable worlds, the promise of the JWST. One of the most exciting possibilities offered by the JWST is the discovery of habitable worlds, planets that have the right conditions to support life as we know it. To date, thousands of exoplanets have been discovered, and a small fraction of these reside in the so-called habitable zone, around their parent stars. This is the region where conditions are just right for liquid water to exist, a crucial ingredient for life. The JWST's observations of exoplanets in the habitable zones of their stars could revolutionize our understanding of planetary habitability. By studying the atmospheres of these planets, the JWST can determine whether they have conditions similar to Earth's, such as a temperate climate, the presence of water, and an atmosphere that could protect life from harmful radiation. One of the JWST's early targets is the TRAPPIST-1 system, a collection of 7 Earth-sized planets orbiting a cool red dwarf star just 40 light-years from Earth. 3 of these planets are located in the habitable zone, making them prime candidates for detailed study. The JWST's ability to analyze the atmospheres of these planets could reveal whether they have the right conditions to support life, providing the first direct evidence of potentially habitable worlds beyond our solar system. The study of exoplanets, particularly those in the habitable zone, has far-reaching implications for our understanding of the universe and our place within it. If the JWST detects biosignatures or signs of habitability on distant planets, it would not only confirm that Earth is not unique in its ability to support life, but it would also open up new questions about the prevalence and diversity of life throughout the cosmos. The search for biosignatures, chemical clues to extraterrestrial life. The search for biosignatures is one of the most exciting and challenging aspects of the JWST's mission. Biosignatures are chemical compounds or phenomena that suggest the presence of life, and they can be detected by analyzing the light that filters through an exoplanet's atmosphere. The JWST's ability to detect these compounds, such as oxygen, ozone, methane, and water vapor, offers a unique opportunity to identify planets that may harbor life. One of the key challenges in the search for biosignatures is distinguishing between biological and non-biological sources of these compounds. For example, methane can be produced by both biological processes, such as microbes, and geological processes, such as volcanic activity. To confirm the presence of life, scientists must look for combinations of biosignatures that are unlikely to occur without biological processes. For instance, the simultaneous presence of oxygen and methane in an atmosphere could indicate life, as these compounds would normally react with each other and disappear unless continuously replenished by living organisms. The JWST's sensitivity to infrared wavelengths makes it particularly well suited for detecting these biosignatures. Unlike visible light, which can be scattered or absorbed by dust and gas. Infrared light can pass through these obstacles, providing a clearer view of distant planets. This allows the JWST to analyze the atmospheres of exoplanets with unprecedented precision, offering the best chance yet of identifying chemical signatures that could indicate life. One of the most promising targets for biosignature detection is Proxima Centauri b, an Earth-sized exoplanet orbiting the closest star to the Sun. While Proxima Centauri b is located in the habitable zone of its star, its atmosphere may be influenced by the intense radiation from its parent star, a red dwarf. The JWST's observations of Proxima Centauri b could provide valuable data on how these factors influence the planet's potential habitability and whether any biosignatures are present. The JWST and the search for techno-signatures, evidence of advanced civilizations. While the search for biosignatures focuses on identifying signs of microbial or primitive life, the JWST also opens the door to the search for techno-signatures, evidence of advanced civilizations. Techno-signatures are artificial signals or markers that could indicate the presence of technologically advanced societies, such as radio waves, light pollution, or even megastructures like Dyson spheres. Although the search for techno-signatures is still in its infancy, the JWST's capabilities make it an important tool for exploring this possibility. By analyzing the light from distant stars, the JWST could potentially detect anomalies that suggest the presence of advanced technologies, such as artificial satellites or energy sources. One of the more speculative but intriguing ideas is the possibility of detecting a Dyson sphere, a hypothetical structure built around a star to capture its energy. Such a structure would block a significant portion of the star's light, creating an observable signature. While this concept remains speculative, the JWST's sensitivity to infrared radiation makes it well suited for detecting such anomalies. The search for techno-signatures represents a new frontier in the quest to understand whether intelligent life exists elsewhere in the universe. While the likelihood of detecting advanced civilizations remains uncertain, the JWST's ability to observe distant stars and planets in detail provides a unique opportunity to explore this possibility. The future of exoplanet research, paving the way for direct imaging. As the JWST continues to explore exoplanets and their atmospheres, it is laying the groundwork for even more advanced methods of studying distant worlds. One of the most ambitious goals in exoplanet research is direct imaging, capturing pictures of exoplanets themselves, rather than inferring their existence from the light of their parent stars. While the JWST is not designed for direct imaging, its observations will provide crucial data for future missions that aim to take images of Earth-like planets. By studying the atmospheres and environments of exoplanets, the JWST will help scientists determine which planets are the best candidates for direct imaging in the future. Future telescopes, such as the proposed Habitable Exoplanet Imaging Mission, HabEx, or the Large Ultraviolet Optical Infrared Surveyor, LUVOIR, will build on the JWST's legacy by capturing images of exoplanets and analyzing their light directly. These missions will use advanced coronagraphs or starshades to block the light from parent stars, allowing scientists to see the faint glow of the planets themselves. The data collected by the JWST will be essential for designing these future missions, helping scientists determine the best targets for direct imaging and providing a clearer understanding of the conditions that make a planet habitable. The JWST is paving the way for a new era of exoplanet exploration, one that could eventually lead to the first images of Earth-like planets beyond our solar system. The implications of JWST's exoplanet discoveries for humanity. The discoveries made by the JWST have profound implications for humanity's understanding of its place in the cosmos. The identification of potentially habitable worlds or the detection of biosignatures would fundamentally alter our perspective on life and the universe. It would confirm that Earth is not unique in its ability to support life and that the conditions for life may be common throughout the galaxy. Such a discovery would raise new questions about the nature of life in the universe. How diverse is life beyond Earth? Could intelligent civilizations exist elsewhere, and if so, how would we communicate with them? These questions, once the domain of science fiction, would become central to scientific inquiry, challenging our understanding of biology, technology, and even ethics. The search for life beyond Earth is not just about finding other planets, it is about understanding our own origins and place in the universe. As Carl Sagan famously said, the Earth is a very small stage in a vast cosmic arena. The JWST's exploration of exoplanets reminds us of the fragility of life on our planet and the importance of preserving our home while we search for others. As the JWST continues to push the boundaries of what we know about the universe, it will inspire future generations of scientists, explorers, and dreamers. The search for life beyond Earth is a journey that has only just begun, and the discoveries made by the JWST will shape the course of this journey for decades to come. Conclusion: the JWST and the future of cosmic exploration. The James Webb Space Telescope represents a new era in our quest to understand the universe. Its discoveries have already challenged long-standing theories, opened new avenues for exploration, and brought us closer to answering some of the most profound questions about our existence. As we continue to explore the cosmos with the JWST, we are reminded of the vastness and complexity of the universe, and of our small but significant place within it. The JWST is not just a scientific instrument, it is a testament to human curiosity, creativity, and the desire to explore the unknown. The future of cosmic exploration holds endless possibilities. From the study of distant galaxies and black holes to the search for life on exoplanets, the JWST is poised to make discoveries that will reshape our understanding of the universe and our place within it. In the words of Carl Sagan, we are star stuff, contemplating the stars. The JWST is helping us continue that contemplation, bringing us closer to the answers we seek and reminding us of the beauty and mystery of the cosmos. The James Webb Space Telescope, JWST, often referred to as the most ambitious astronomical project in human history, is named after James Edwin Webb, a man whose visionary leadership played a crucial role in shaping the United States space exploration efforts during the 1960s. While Webb may not be as widely recognized as some of the astronauts or scientists involved in the space race, his impact on NASA and the space program was profound. He is credited with steering the agency during one of its most critical and transformative periods, ensuring that it became not only a vehicle for space exploration but also for scientific discovery. James Webb served as NASA's second administrator from 1961 to 1968, a period that saw both tremendous achievements and significant challenges for the agency. Under his leadership, NASA was not only focused on landing a man on the moon but also on expanding scientific knowledge through space-based research. Webb believed in a broad vision for NASA, one that included both human spaceflight and scientific missions, and this philosophy is reflected in the telescope that bears his name today. Early life and career of James E. Webb. James Edwin Webb was born on October 7, 1906, in Tally Ho, North Carolina. Raised in a rural environment, Webb showed early promise in both academics and leadership, qualities that would carry him through a distinguished career in public service. He earned a law degree from George Washington University and began his career in government during the Great Depression, working in various roles that included legislative aide and assistant to the Undersecretary of the Treasury. Webb's public service career was interrupted by World War II, during which he served as a pilot in the Marine Corps. After the war, he returned to government service, where his reputation as a highly capable administrator grew. Before his time at NASA, Webb held various positions in both the public and private sectors, including serving as Director of the Bureau of the Budget and Undersecretary of State in the Truman administration. His experiences in these roles helped Webb develop a deep understanding of governmental operations, particularly the management of large, complex organizations, skills that would prove invaluable during his tenure at NASA. Leading NASA through the space race. When James Webb took the helm at NASA in 1961, the United States was in the midst of the Cold War and locked in an intense space race with the Soviet Union. The Soviet Union had already achieved a number of significant space milestones, including the launch of Sputnik in 1957, the first artificial satellite, and the historic flight of Yuri Gagarin, the first human in space, in 1961. In response, the U.S. government, led by President John F. Kennedy, made it clear that winning the space race was a top priority. Kennedy's famous speech in 1961 set the ambitious goal of landing a man on the moon before the end of the decade, a challenge that would come to define Webb's time at NASA. Webb embraced this challenge, overseeing the development of the Apollo program, which would eventually culminate in the successful moon landing of Apollo 11 in 1969. Though Webb resigned from NASA before the actual landing, his leadership and vision were critical in laying the groundwork for the program's success. He managed NASA during the formative years of the Apollo missions, making difficult decisions and guiding the agency through technical and political challenges. One of Webb's greatest strengths was his ability to navigate the complex relationship between NASA and the U.S. Congress. He ensured that the space agency received the necessary funding and political support to pursue its ambitious goals, which included not only landing a man on the moon but also a wide range of scientific missions. Webb was deeply committed to the idea that space exploration was not just about national prestige or military superiority but also about advancing human knowledge. The vision for science and exploration. While the Apollo missions and human spaceflight programs understandably garnered much of the public's attention during Webb's tenure, he was equally passionate about NASA's scientific endeavors. Webb believed that space exploration should be a vehicle for scientific discovery, and he made sure that NASA's budget included substantial funding for robotic missions, space telescopes, and other scientific instruments. Under Webb's leadership, NASA launched a number of groundbreaking scientific missions. These included the Mariner missions to Venus and Mars, which provided the first close-up images of other planets, as well as the development of early space observatories. Webb understood that the scientific exploration of space would yield benefits far beyond the immediate goals of the space race. He believed that space-based research could unlock new understanding about the origins of the universe, the nature of the solar system, and the possibility of life beyond Earth. One of Webb's lasting legacies is the balance he struck between human spaceflight and scientific exploration. He saw NASA as an organization that could pursue both goals simultaneously, and his support for scientific research laid the foundation for future space observatories like the Hubble Space Telescope and, eventually, the James Webb Space Telescope. Webb's departure and legacy. James Webb's time at NASA came to an end in 1968, a year before the historic Apollo 11 moon landing. His decision to resign was driven in part by the political climate of the time. The Apollo program had suffered a significant setback with the tragic loss of the Apollo 1 crew in a launch pad fire in 1967, and Webb faced intense political scrutiny. Though the agency was on track to achieve Kennedy's goal of landing a man on the moon, Webb felt it was time for new leadership to guide NASA through the final stages of the Apollo program. Despite stepping down before the culmination of Apollo's success, Webb's legacy within NASA was secure. His contributions to space exploration, particularly his vision of a space agency that balanced both human exploration and scientific discovery, have had a lasting impact on the direction of NASA. In recognition of his contributions, NASA chose to name its next-generation space telescope after Webb, a fitting tribute to a man who believed so deeply in the power of science and exploration. The naming of the James Webb Space Telescope. The decision to name NASA's most ambitious space observatory after James Webb was not made lightly. The telescope, originally known as the Next Generation Space Telescope, NGST, was conceived as the successor to the Hubble Space Telescope. Its mission was to explore the universe in unprecedented detail, looking back to the very first stars and galaxies that formed after the Big Bang. Given the scope of this mission, NASA sought a name that would reflect the boldness and vision of the project. In 2002, NASA Administrator Sean O'Keefe announced that the telescope would be named after James Webb, in recognition of his leadership and his enduring commitment to both space exploration and scientific discovery. This decision was not without controversy, as some believed that the telescope should be named after a scientist or astronomer, rather than an administrator. However, Webb's champions argued that his contributions to the space program, particularly his support for science, made him a fitting namesake for an observatory designed to expand our understanding of the cosmos. The James Webb Space Telescope represents the culmination of decades of technological innovation and scientific ambition, and its mission is in many ways a continuation of Webb's legacy. Just as Webb believed in using space exploration as a tool for scientific discovery, the telescope named in his honor is designed to unlock the mysteries of the universe, from the formation of the first galaxies to the search for habitable planets. Conclusion: Webb's enduring impact on space exploration. James E. Webb's tenure as NASA's administrator was marked by some of the most significant achievements in the history of space exploration. His leadership during the Apollo program, his advocacy for scientific research, and his ability to secure political and financial support for NASA's missions all contributed to the success of the space program in the 1960s and beyond. The James Webb Space Telescope, which now bears his name, is a fitting tribute to a man who understood the importance of both human exploration and scientific discovery. The legacy of James Webb continues to inspire today's space explorers and scientists. His vision of a space agency that balances the pursuit of knowledge with the desire to push the boundaries of human exploration remains at the core of NASA's mission. As the James Webb Space Telescope peers deeper into the cosmos than ever before, it carries forward Webb's belief that space exploration is not just about reaching new frontiers, but about understanding the universe and our place within it. The telescope named in his honor will no doubt reveal new wonders of the universe, wonders that Webb himself would have been proud to see. His enduring impact on space exploration serves as a reminder that behind every great mission, there is a visionary leader whose decisions shape the course of history. The James Webb Space Telescope, JWST, is not only a tribute to the legacy of James E. Webb but also a feat of engineering and scientific innovation. Its design, construction, and eventual deployment are the result of decades of research, collaboration, and perseverance by scientists and engineers across the globe. Often described as the most ambitious space observatory ever built, the JWST has pushed the boundaries of what is possible in space technology, allowing humanity to explore the universe in unprecedented detail. The JWST's mission is to explore the universe's earliest galaxies, peer into the birthplaces of stars and planets, and search for signs of life in the atmospheres of distant exoplanets. To achieve these ambitious goals, the telescope had to be equipped with cutting-edge technology, some of which had never been used in space before. From its massive segmented mirror to its advanced infrared instruments, the JWST represents a technological leap forward in our ability to study the cosmos. The JWST's segmented mirror, a giant leap in astronomy. One of the most striking features of the James Webb Space Telescope is its massive, gold-coated primary mirror. At 6.5 meters, 21 feet, in diameter, the JWST's mirror is nearly 3 times larger than that of the Hubble Space Telescope, enabling it to collect much more light and see farther into the universe. However, building a mirror of this size posed a unique challenge. It had to be lightweight enough to be launched into space, yet precise enough to capture extremely faint light from distant galaxies. The solution was an innovative design that uses 18 hexagonal mirror segments made of beryllium, a lightweight and strong metal. Each segment is coated with a thin layer of gold to improve its ability to reflect infrared light, the primary wavelength that JWST observes. These segments fit together to form a single, large, curved mirror that focuses light onto the telescope's scientific instruments. One of the most impressive aspects of the mirror is its ability to unfold and align itself in space. Because the JWST's mirror is so large, it could not fit into the launch vehicle fully extended. Instead, it was folded up like origami during launch and then unfolded in space, a process that required precise coordination and engineering. The mirror's alignment, known as wavefront sensing and control, is so accurate that it can detect differences in the position of the mirror segments as small as 50 nanometers, about 1/10,000th the width of a human hair. This innovative segmented design, coupled with advanced alignment technology, allows the JWST to observe some of the faintest and most distant objects in the universe. It is this ability to collect and focus more light that makes the JWST capable of looking further back in time than any previous telescope, capturing light from galaxies that formed just a few 100 million years after the Big Bang. Observing the universe in infrared, the power of the JWST's instruments. While the JWST's primary mirror is crucial to its ability to observe the universe, it is the telescope's suite of scientific instruments that enables it to gather detailed data about distant objects. Unlike the Hubble Space Telescope, which observes primarily in visible and ultraviolet light, the JWST is optimized for infrared observations. This is because the universe's most distant galaxies, which the JWST is designed to study, have their light stretched into the infrared part of the spectrum due to the expansion of the universe, a phenomenon known as redshift. The JWST is equipped with 4 main instruments, each designed to capture different aspects of infrared light and provide a comprehensive view of the cosmos. 1. Near-infrared camera, NIRCam. NIRCam is the telescope's primary imaging instrument, designed to observe in the near-infrared range, from 0.6 to 5 microns. It is responsible for capturing detailed images of distant galaxies, star-forming regions, and exoplanetary systems. NIRCam's ability to observe faint objects in great detail makes it essential for studying the early universe and finding some of the first galaxies to form after the Big Bang. 2. 3. Near-infrared spectrograph, NIRSpec. NIRSpec is designed to analyze the light from distant objects, breaking it down into its component wavelengths to determine the chemical composition, temperature, and motion of stars, galaxies, and planets. This spectrograph can observe up to 100 objects simultaneously, making it an incredibly powerful tool for studying large-scale structures like galaxy clusters and for analyzing the atmospheres of exoplanets. 4. 5. Mid-infrared instrument, MIRI. MIRI operates at longer wavelengths, from 5 to 28 microns, allowing it to observe cooler objects that emit most of their radiation in the mid-infrared range. This includes distant, dust-obscured galaxies, forming stars, and protoplanetary disks. MIRI is also crucial for studying planets and moons within our own solar system, as its sensitivity to heat makes it ideal for detecting thermal emissions from these objects. 6. 7. Fine guidance sensor / near-infrared imager and slitless spectrograph, FGS/NIRIS. This instrument serves 2 purposes. It helps the JWST maintain precise pointing and stability during observations, and it provides additional imaging and spectroscopic capabilities. NIRIS is particularly well suited for studying exoplanets and searching for signatures of water, methane, and other molecules that could indicate the presence of life. 8. Together, these instruments allow the JWST to observe a wide range of celestial phenomena, from the formation of the first stars and galaxies to the detection of potential biosignatures on exoplanets. The ability to observe in the infrared gives the JWST a significant advantage over previous telescopes, as it can peer through clouds of dust and gas that would otherwise obscure these objects in visible light. The Sunshield, protecting the JWST's instruments. To make the most of its infrared capabilities, the JWST needs to operate at extremely cold temperatures, close to absolute zero. Infrared light is essentially heat radiation, and in order to detect faint heat signals from distant galaxies and exoplanets, the telescope itself must remain cold enough that its own heat does not interfere with observations. This is where the JWST's innovative Sunshield comes into play. The Sunshield is a 5-layer structure, roughly the size of a tennis court, that protects the telescope from the heat of the Sun, Earth, and Moon. Each layer of the Sunshield is made of a special material called Kapton, which is coated with aluminum and silicon to reflect sunlight and dissipate heat. The layers are arranged in such a way that the heat is radiated away from the telescope, allowing its instruments to cool to the necessary operating temperature of around -233 degrees Celsius -388 degrees Fahrenheit. The Sunshield is perhaps one of the most critical and complex components of the JWST, as it had to be carefully designed to fold up during launch and then unfold in space. This process involved the deployment of hundreds of mechanisms, cables, and springs, all of which had to work perfectly to ensure the telescope's instruments could remain shielded from heat. The successful deployment of the Sunshield was a major milestone in the JWST's journey, marking the beginning of its scientific mission. L2, the perfect location for a space observatory. The JWST's mission is not just about advanced technology, it also involves placing the telescope in the ideal location to observe the universe. Unlike the Hubble Space Telescope, which orbits the Earth, the JWST is positioned at a point in space known as the second Lagrange point, L2, located about 1.5 million kilometers, 930,000 miles, from Earth. This location offers several key advantages for an infrared observatory. L2 is a point where the gravitational forces of the Earth and Sun balance, allowing the JWST to remain in a stable position relative to both bodies. This means the telescope can maintain a continuous orientation with respect to the Sun, Earth, and Moon, keeping its sunshield properly aligned to block heat and light from these sources. Additionally, being so far from Earth allows the JWST to avoid the infrared radiation emitted by our planet. Even though the JWST's instruments are highly sensitive, the heat from Earth could interfere with its ability to detect faint infrared signals from distant galaxies. By placing the telescope at L2, NASA ensured that it would have a clear, unobstructed view of the cosmos. The choice of L2 also provides the JWST with an uninterrupted view of the sky. Unlike telescopes in low Earth orbit, which must deal with the shadow of Earth blocking part of the sky, the JWST can continuously observe a wide field of view, allowing it to capture long exposures and gather more light from distant objects. The challenges and triumphs of the JWST's journey. The journey of the James Webb Space Telescope from concept to launch was anything but straightforward. The project faced numerous technical challenges, budget overruns, and delays over its nearly three-decade development. Originally conceived in the 1990s as the successor to Hubble, the JWST's launch date was initially set for 2007, but a series of design changes, cost increases, and engineering difficulties pushed the launch back multiple times. One of the biggest challenges was the complexity of the telescope's design. From the segmented mirror to the sunshield to the infrared instruments, each component had to be engineered with extreme precision, and many of the technologies involved were being developed for the first time. Testing these components to ensure they would work in the harsh environment of space took years, and unexpected issues often arose, requiring additional time and resources to address. Despite these setbacks, the JWST team persevered, and the project finally reached completion in 2021. The telescope was launched on December 25, 2021, aboard an Ariane 5 rocket from French Guiana. The successful deployment of the JWST's mirror and sunshield in space marked a historic achievement in space exploration, one that was celebrated by scientists and engineers around the world. The future of cosmic discovery. With the James Webb Space Telescope now fully operational, humanity stands on the brink of a new era in cosmic exploration. The JWST is expected to operate for at least 10 years, during which it will collect vast amounts of data that will revolutionize our understanding of the universe. From studying the birth of stars and galaxies to searching for life on distant exoplanets, the JWST is poised to make discoveries that will reshape our understanding of the cosmos. The telescope's ability to look deeper into space, and thus further back in time, than any previous observatory will provide new insights into the earliest moments of the universe. It will allow scientists to explore the formation of the first galaxies and stars, offering clues about how the universe evolved from a hot, dense state to the vast, complex cosmos we see today. In addition to its contributions to cosmology, the JWST will also play a critical role in the search for life beyond Earth. By studying the atmospheres of exoplanets in unprecedented detail, the JWST could provide the first direct evidence of habitable conditions, or even life itself, on other worlds. As the JWST embarks on its scientific mission, it carries forward the legacy of James Webb, a man who believed in the power of space exploration to expand human knowledge. The discoveries made by this remarkable telescope will inspire generations of scientists, astronomers, and explorers, pushing the boundaries of what we know about the universe and our place within it. Conclusion: a new horizon for humanity's cosmic journey. The James Webb Space Telescope represents not just a triumph of engineering and science, but a new chapter in humanity's quest to understand the universe. Its journey from conception to launch, spanning nearly 3 decades, is a testament to human perseverance, vision, and the drive to explore the unknown. Now fully operational, the JWST stands as the most advanced space observatory ever built, poised to revolutionize our understanding of the cosmos. Through its ability to peer deeper into space and further back in time than any previous telescope, the JWST will allow scientists to unravel some of the universe's most profound mysteries. From observing the first stars and galaxies that formed after the Big Bang to probing the atmospheres of distant exoplanets in search of life, the telescope's discoveries will reshape our knowledge of the universe's origins, its structure, and its future. The JWST embodies the spirit of exploration that has driven humanity to look beyond our planet and seek answers to the fundamental questions of existence. It carries forward the legacy of James E. Webb, whose leadership helped NASA balance human exploration with scientific discovery during the space race. In his honor, the telescope's mission reflects a commitment to understanding the universe through rigorous science, curiosity, and a belief in the transformative power of knowledge. As the JWST embarks on its journey of discovery, it will not only deepen our understanding of the cosmos but also inspire future generations to continue exploring the stars. Each new revelation will bring us closer to comprehending our place in the vast, intricate universe we call home, reinforcing the truth that we are all part of something much greater. The future of cosmic exploration is filled with limitless possibilities, and the James Webb Space Telescope is the key to unlocking those mysteries. In the words of Carl Sagan, the cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. Through the JWST, we continue this ancient endeavor, reaching out into the depths of space, driven by the innate human desire to know, to seek, to discover, and to understand.